When people hear HVAC, they often picture a thermostat and a fan. In a hospital, that picture is much too small. HVAC is clinical infrastructure. It controls ventilation, filtration, pressure, temperature, and humidity while removing equipment heat every hour of every day. The useful way to understand it is as one connected chain. Utilities enter the campus. Central plants make steam and chilled water. Pumps distribute energy. Air handling systems treat and move air. Controls coordinate the equipment. And people verify that the room actually received what was intended. We will follow that chain, ask what can go wrong, and finish with the operating habits that protect patient care, research, reliability, and energy performance. Pick one patient room and work backward. The room needs the right temperature, humidity, airflow, and where required, pressure relationship. A variable air volume terminal meters airflow and may add reheat. The air handling system filters, heats, cools, dries, humidifies, and pushes the air. Heating water and chilled water loops connect that equipment to the central plant. The plant, in turn, depends on electricity and fuel. Now multiply that chain across roughly 5.5 million square feet, about 15 buildings, more than 40 closed hydronic systems, hundreds of air handling systems, thousands of variable air volume terminals, and thousands of building automation points. The plant includes 6 boilers, 11 chillers, 19 emergency generators, and many shared dependencies. Annual campus utility cost is about $43 to $44 million, roughly $39 million for electricity, $3 million for natural gas, and $1 to $2 million for fuel oil. Those are total campus utilities, not an HVAC-only allocation, and electricity is close to 90% of the total. The point is not just scale. It is coupling. A sensor, valve, damper, pump, fan, control sequence, power source, or human response can affect the room several systems away. Steam begins as a water quality problem. Treated makeup water passes through softeners. The planned dealkalizer sits after those softeners and before the feedwater receiver and deaerator, reducing alkalinity before the water reaches the boilers. Returned condensate joins the treated makeup water in the receiver. The deaerator heats the feedwater and removes dissolved gases. An economizer recovers heat from flue gas, and 6 boilers produce up to 360,000 pounds of steam per hour. The campus heater operates at about 125 pounds per square inch gauge. That steam supports heating, humidification, sterilization, and steam turbine chillers. Condensate return is not waste plumbing. It recovers heat, water, and treatment value. And the dealkalizer is not a savings claim. It is a testable hypothesis. Lower feedwater alkalinity should generate less carbon dioxide from that alkalinity, which may improve condensate conditions and reduce chemical use, blowdown, makeup water, and fuel. But measure before promising. Establish a baseline, commission the equipment, trend condensate acidity and corrosion, and compare treatment, blowdown, water, and fuel after startup. The engineering lesson is simple. Verify the whole steam and condensate system, not just the new vessel. A chiller does not make cold. It moves heat. Building coils absorb heat from the air, and chilled water carries that heat back to the plant, typically around 42 degrees Fahrenheit leaving the plant and 56 degrees returning, although operating targets can reset. Inside the chiller, a separate refrigerant circuit runs from evaporator to compressor, condenser, and expansion device. Then a third circuit, condenser water, carries the rejected heat outdoors. Water may arrive from the cooling tower near 85 degrees and return to the tower near 95. The tower belongs to the condenser water circuit, not the refrigerant loop. Across 11 chillers, the installed capacity is about 20,900 tons. Efficiency depends on choosing the right machines, operating them near efficient part load points, managing lift, coordinating towers and pumps, resetting temperatures when conditions and clinical needs permit, and controlling peak electrical demand. The campus can also dispatch between electric and steam turbine chillers when equipment availability and utility conditions support it. Each loop has a different fluid and job, but performance appears only when the 3 circuits operate as one heat rejection chain. Hydronic systems are the campus bloodstream. Closed chilled water, heating water, dual temperature, and specialty laboratory loops circulate the same treated fluid. Heat exchangers pass energy between plant and building systems while keeping the fluids separate. Pumps with variable frequency drives should move only the flow the system needs. Coils deliver the heating or cooling, and the return temperature difference tells us whether that energy was actually used. Valves, strainers, sensors, expansion control, and water quality all matter. Condenser water is different. It is open to the atmosphere at the cooling tower, so it needs dedicated treatment, monitoring, cleaning, and maintenance. A pump command alone proves nothing. Verify flow, pressure, temperature difference, valve position, and the condition at the coil. An air handling system is a treatment train. Outdoor air mixes with return air where the design permits. Filters remove particles in stages. Preheat protects coils and tempers cold air. The cooling coil lowers temperature and removes moisture. Humidification adds moisture where required. A supply fan, usually controlled by a variable frequency drive, moves the treated air to the space. Dampers set the mixture, valves set coil capacity, and sensors tell the sequence what happened. Some systems use 100% outdoor air, higher filtration, or dedicated exhaust, depending on the space. At the zone, a variable air volume box reads temperature, modulates its damper, holds the permitted ventilation minimum, and reheats when needed. But comfort is not always the governing rule. Operating rooms are generally maintained positive to adjacent areas. Airborne infection isolation rooms are negative, so air flows in. Protective environment rooms are positive, so air flows out. Laboratories follow the hazard assessment and program. Exact ventilation, pressure, temperature, humidity, filtration, and exhaust requirements vary with code, design, and use, including the applicable healthcare ventilation standard and infection control guidance. So a comfort-saving sequence must never override the clinical airflow requirement. The equipment is only correct when the actual room relationship is correct. Think of the building automation system as a loop, not a remote control. First, sense temperature, humidity, pressure, airflow, equipment status. Second, decide, compare set points, apply sequences, resets, staging, and alarms. Third, act, move valves and dampers, change variable frequency, drive speed, start equipment, or stage capacity. Fourth, and this is the step people skip, verify. Trend the result, calibrate the sensor, and check the field condition. A command does not prove the actuator moved, and an actuator position does not prove the room responded. Here's how a small failure travels. A sensor drifts. The controller makes the wrong decision. A valve, damper, drive, or piece of equipment takes physical action. The room's temperature, humidity, airflow, or pressure drifts. Then patient care, research, comfort, staffing, energy, or room availability is affected. Operations sees alarms, troubleshooting labor, call-ins, or emergency response. Financially, the same problem may create simultaneous heating and cooling, excessive fan or pump speed, and avoidable cost. Major equipment can look healthy while the system performs incorrectly. Trends, calibration, field checks, and leading indicators catch that gap before the room becomes the alarm. The first energy rule is a guardrail. Never trade required ventilation, pressure, temperature, humidity, filtration, or redundancy for savings. Within that boundary, the biggest opportunities are operational. Sequence chillers and boilers so the efficient combination runs. Reset chilled water, condenser water, and pressure targets when outdoor conditions, space requirements, and system design permit. Use variable frequency drives to match fan and pump output to demand instead of wasting energy across throttled dampers and valves. Recover flue gas and condensate heat, and keep steam traps and return systems healthy. Retune sequences and use fault detection to find simultaneous heating and cooling, failed resets, and sensors or actuators that lie. Demand response, approved non-critical setbacks, gas interruption readiness, and dual fuel capability can add flexibility. But prove outcomes with measurement and verification. The load curve shown here is illustrative, not measured campus data. The actual portfolio is roughly $43 to $44 million per year, with electricity dominant, so peak demand, chiller dispatch, fan power, pump power, and tower operation deserve attention. Reliable operation and good measurement are the foundation of credible savings and emissions reduction. Reliability is not a piece of equipment. It is a practice owned by an approximately 80-person plant operations team, 9 managers and 71 staff, working across one interconnected campus. They monitor building automation trends, conduct rounds, and check water chemistry. They maintain equipment through preventive and predictive work, cleaning, lubrication, testing, and calibration. They respond to alarms and emergencies around the clock. They change systems safely using methods of procedure, lockout and tagout where applicable, shutdown planning, communications, contingency steps, and restoration verification. Then they improve the system through commissioning, compliance work, trend review, capital planning, critical spares, and training. Before a shutdown, ask, what spaces depend on this asset? What redundancy is real today? Who must know? And how will restoration be proven? After the work, do not stop at the equipment started. Confirm the intended flow, pressure, temperature, humidity, airflow, alarms, safeties, and room condition. That discipline is what turns equipment and controls into safe, reliable service 24 hours a day, 7 days a week, 365 days a year. The whole presentation reduces to one connected system and 3 priorities. First, protect care, maintain the environmental conditions the clinical and research programs require. Second, sustain continuity, operate safely around the clock, understand dependencies, and verify recovery after change or failure. Third, manage cost and emissions, improve sequencing, controls, recovery, and flexibility, then verify the result across a $43 to $44 million utility portfolio. The leadership priority is to invest in reliable equipment, trustworthy sensors and controls, disciplined operations, trained people, and measurement. When those pieces work together, HVAC becomes what it really is, not background comfort machinery, but core clinical infrastructure.